online seminar on water waves. Thank you very much for joining us today. I'm the chairperson for today's seminar, Sunao Murashige from Ibaraki University. Today, we have two speakers. The first speaker is Dr. Ricardo Barros from Loughborough University. And the title of the lecture is the large amplitude mode 2 internal solitary waves in 3-layer flows. Okay, Dr. Barros, the stage is yours, please.
Thank you very much. Now, it's a pleasure delivering this talk. It's a pity we haven't seen each other in person, right, last year. But the pandemic told us to do differently. So, yeah, so this is a work that I'll be presenting that is a result of the work that we have done with Woo-Young Choi, Paul Milewski, and Alex Dowak more recently. So Alex is a postdoc at the University of Bath, working with Paul and I in this moment. So basically, for what is going on? Okay. So for those in the audience who haven't heard anything about internal waves, let me just tell you that first, interfacial waves are waves appearing at the interface of two liquids, okay? And in the ocean, these two liquids could be, for example, a salted layer of water, okay, and a less salted layer of water, okay? Or, if, for example, especially in summer periods, you will have, for example, a warmer layer of water above a colder layer of water, okay? So there will be an interface, and at the interface, you will have some huge features, okay, exceeding, for example, 100 meters, okay? And these are waves, for example, quite long, okay, wavelengths of order of kilometer. I mean, they propagate without changing its shape for long distances. I mean, up to 25, 35 kilometers, and they move in slow motion, okay? Now, the thing is that the, I mean, amplitudes were up to 140 meters were actually recorded in the South China Sea. So, I mean, for comparison, I just put here some iconic buildings, for example, like the Gherkin that we have here in London. So 179 meters, okay? So the waves, the biggest, at least recorded up to now, it's up to 140, okay? So this is huge, huge features, okay? Features. So, I mean, what do they look like from space? So they can be detected from satellite by using this kind of backscattering images where you actually see, so these kind of SAR images, synthetic aperture radar, when you look at these pictures, you see these kind of wrinkles at the surface, okay? So these here like ring waves, okay? Here similarly in the Red Sea, so this is the Gibraltar, by the way. This is the Red Sea, and these wrinkles here is the sign of some internal wave activity at the interface, okay? And these are called the internal wave signatures, okay? So they have been, I mean, when you look at this, so for example, this is a map compiled by the Office of Naval Research, and each one of these red dots, okay, is an internal wave activity region, okay? So what you will remark is that basically they are coastal areas phenomena, okay? So they appear close to the coast, okay? Or in places like Azores, okay? Where of course the depth of the ocean decreases there because you have all these islands there, okay? So, I mean, there are plenty of places in the world where you have internal waves, okay? And in particular, the South of China Sea has a lot of interest, okay? So the majority of internal wave observations are what we call the first paraclinic mode or mode 1 waves, okay? And typically when you look at this, so for example, this is I mean, in situ measurements from Duda and all in 2004. And what you have here, you have all these isopycnoclines lines, or actually it's isothermals, okay? So this is by temperature in this case. And what you see is a very fast transition from this colder water to warmer water, okay? And the yellow line is what we will call, for example, the thermal plane, which is the sharp separation of the two layers, okay? And when you put together, for example, the KDV profile, which is this square profile that everyone knows, you see how poor is the agreement with this kind of more elongated wave that you have in the ocean, okay? So this being what we call a mode 1 wave, all the displacements of the isopycnals are aligned, okay? So everything points downwards in this case, okay? So this is a characteristic of what we call the mode 1 waves, okay? And this can be accurately described by strongly nonlinear two-layer models, okay? Provided the transition layer is sharp enough, okay? So that's the simplest system you can think of to study these kind of waves. So you take two fluids, okay, homogeneous layers, okay, with constant density ρ1, ρ2. You put, for example, so you assume something stably stratified, which means that the heavier fluid sits on the bottom, okay, the lighter fluid sits on the top, and then you put this in the interface in motion, okay, and then you will see the dynamics for this thing. So the Miyata-Choi-Kamasa model has been particularly successful in describing these large amplitude solitary waves, observed both in lab experiments and predicted by numerical solutions for other equations. So in terms of asymptotic modeling, what the models suppose is long wave approximation. So you will have a small parameter, which is the epsilon, which is a typical height divided by a typical length, and this is considered small enough. Then you have to assume that the leading order of the horizontal velocity is independent of the vertical coordinate set. And of course, as I said, we are only working with things which are stably density stratified, okay? Which means that the heavier fluid always sits on the bottom, okay? So here, a few more considerations that, for example, the two layers have comparable depth, okay? And we don't impose any weakly nonlinear assumption on the wave amplitude, okay? So wave amplitude over the total depth, for example, can be of order 1, okay? So this is important. And this is what the model looks like. So the first equation is just the mass conservation law. So notice that this is the U bar is a depth average horizontal velocity field, okay? And then you have a momentum equation where this kind of d dt is just the material derivatives according to each flow velocity. And g is gravity, zeta is the interface displacement, and p is the pressure at the interface, okay? And now these terms on the right-hand side, okay, are just accounting for the dispersive effects, okay? So if I just kill this right-hand side here, these will be what you call the Saint-Venant equations or shallow water equations, okay? So hyperbolic for small relative speeds, okay, or velocities across the layers. But because we have a right-hand side, then you have dispersive properties, and you have solitary waves, okay? So let's see. Solitary waves for the Miyata-Choi-Kamasa model are governed by a Hamiltonian system with 1 degree of freedom. So this is the Hamiltonian, zeta x squared is some kind of minus potential, okay? And the potential depends, of course, on the zeta, which is the interface displacement, and you have the physical parameters and the wave speed, okay? So what you have here is the paper by Kamasa and al. In 2006, comparing on the left panels, you will see the comparison between the waves for the MCC and for the Euler, okay? So as you can see, the agreement is quite remarkably good, okay? Especially for large amplitude waves, where it's very difficult to distinguish where the Euler and the MCC lie. I mean, they are basically the same. Now, in terms of experiments, so this is on the panels on the right, this is slightly different story. Because you can see on the front of the wave, which is this part here, the agreement is pretty good as well, okay? But especially for large amplitude waves, then you see that the agreement is not that great at the back of the wave crest, okay? And this is a result of the I mean, the Kelvin-Helmholtz instability, the bellows that will start appearing and shedding away from the wave at the back. Okay, so this is something, I mean, implicitly associated with the time-dependent problem. Okay, so but I mean, so the good thing is, as I said, for example, we expect a very good agreement up to very large amplitude waves. Okay, and actually, when you look at the conjugate states for MCC or Euler, they are precisely the same. Okay, which means that if you have a kink, so it's basically a solution that will connect two different equilibria. These equilibria are exactly the same for the asymptotic modeling by MCC or Euler. Okay, they're exactly the same, and the maximum wave amplitude is exactly given by this. Okay, at this with the maximum wave speed. Okay. And beyond this maximum wave speed, there are no solutions, okay? Both for MCC and Euler. Now, let's look at, so as I said, so far we have just covered the mode 1 waves. Now, mode 2 waves, okay, are quite different from mode 1. So first of all, they are less energetic than mode 1 waves, but they still may have a significant effect on eroding the Pichnell line, okay? And in particular in the fluxes of heat and neutrons in the water column. And as we will see, I mean, you have a much richer family of solutions here. Okay, so for example, what you have here is a train of mode 2 waves. So this was done in a lab, in a tank by Magda Carr and co-authors. And this bulge of water is what we call some kind of convex mode 2 wave, okay? And you have some more on the back. And here, for example, although, so the mode 1 waves, all the displacements of the isopycnals were pointing to the same direction. Here, one points to upwards and the other one points downwards, okay? Or the other way around. I mean, if you have a concave wave, okay, then in that case, the interface above is pointing downwards and the one below is pointing upwards, okay? And in the same way we did the study for mode 1 waves in a 2-layer flow, I would like to study mode 2 waves in 3-layer flows, okay? 3, because 3, if you are using a layered model, is the minimum number of layers required to support these waves, okay? So let's do that. So let's look first some existence results. So the existence of mode 2 internal solitary waves has been rigorously established for the fully nonlinear theory, meaning Euler, by these authors, Tung and al., only under Boussinesq approximation and when the domain and density stratification are horizontally symmetric. So this is the only setting where they could actually prove analytically the existence of such waves, okay? But unfortunately, these conditions are too restrictive, right? I mean, you cannot find these. It's very unlikely to find these in the ocean, right? Or in the field or where most observations are made, right? But still, these are the conditions that you often find in the majority of lab, theoretical, and numerical studies, okay? And the reason is that when symmetry is broken, and it can be broken by in many ways, so by geometry, density stratification, or simply by considering, for example, non-Boussinesq effects, okay? And when you do that, then asserting whether or not such waves exist becomes a non-trivial problem, okay? And this is what you expect to find. These are called generalized solitary waves. So they have been found, for example, in a 3-layer flow by Van den Broek and Turner, for example, in 92. So you see here just half of the solution. So you have here the crest. So this is a lower interface. And then, you know, I mean, you would expect a classical solitary wave. You would expect this to decay to some point, right, at infinity. Here, there is no such thing. So there's some kind of non-decaying oscillatory tails, okay? And similarly, in the ocean, I mean, this is a picture taken from this paper of Achilles and Grimshaw, where you don't see anything. So this wave is actually traveling to the left, okay? So everything is clean here from the left. Here you see it seems to have some kind of 3 humps, but then you have these kind of oscillations on the back, okay? When I first saw this figure, I was intrigued by this because I wanted to know these irregularities here at the crest. I mean, could these be part of the solution, or is it just some noise caused by, for example, the Kelvin-Helmholtz instability? I was not sure of this, right? But anyway, so the existence of classical Salter waves decaying to zero to infinity cannot, however, be simply ruled out, right? So although we have seen all this evidence of solutions like that, right? My point is that you shouldn't simply rule out the classical things which decay at infinity, okay? So this is the premise we start to look at the study. I mean, to look at the classical solitary wave solutions in this kind of strongly nonlinear model. So as I said, we will require 3 layers. And then this is just an extension of the 2-layer MCC model, the Miyata-Choi-Kamasa model, okay? So exactly the same considerations, okay? So this is a sketch here. So we are looking at the flow between 2 rigid walls. This is at height, for example, h1, and this is at height minus h2 minus h3. Then you have 3 layers, okay? So 3 homogeneous liquids there. So one with constant density ρ1, which is lighter than ρ2, which is lighter than ρ3, okay? So stably stratified. Then you have 2 interface displacements, zeta1 for the top layer, zeta2 for the lower layer, okay? And then this is just, for example, we use small h index I, sub I, as being the thickness of each one of these layers, okay? Which of course will depend on Xn time. Okay, so I mean, the idea to generalize the MCC is exactly the same. So we use exactly the same conditions. So we use a long wave approximation. So this is a long wave model, weak horizontal vorticity, okay, and stably stratified, okay. So what we'll use is just an extension of the Miyata-Choi-Kamasa model proposed to 2 layers from 2 to 3. And this generalization has been done by Woo-Young Choi in 2000, but by others as well. For example, Percival, Coulter, and Holm in 2008. Okay. So the model is this one. Okay. So on the first one is just the mass conservation law. Again, still written in terms of the depth average velocities. Okay. And then you have a momentum equation. Again, the right-hand side, if I decide just to remove it and set it to 0, then these are just the shallow water equations, okay, for a 3-layer flow. If you decide to include them, well, then you have these AI, BI defined here, okay, which accounts for the dispersive effects, okay. So here, PI are the pressures at each one of the interfaces. And of course, it doesn't really matter where we look at, because we can place this pressure, or we can consider this pressure at any level, okay? Because you have a recursion formula to relate them, okay? Pi plus 1 equals Pi plus this correction here, okay? So this is the PDE model. And then my idea here is to cover from linear up to strongly nonlinear theory, okay? So first, linear, okay, linear theory. What does it tell? What does the linear theory tells us about this model, okay? So when we linearize about the equilibrium, the 0 equilibrium, okay, we look for the dispersion relation, and then we have a big quartic, okay, b quadratic, sorry. So this is a quartic, which is a b quadratic, okay? So there's no terms in c cube or c, okay? And what you can prove, so what you have here is all the parameters, okay, plus the wave number k, okay? And I mean, there are too many parameters, okay? But still, it is kind of, it can be proved that all the roots are real, okay? And on top of that, you have 2 branches of solutions, okay? So one which starts at, so there are 2 roots to that equation. One I will call, for example, so this is so here, this is the wave number on the lower axis. On the vertical axis is the wave speed, okay? So you have at so you have all these 2 roots, as I said, okay? And this branch, the lower branch, is what we call the slow mode, and the faster branch here above is given here. Okay, so what you have here is the comparison between Euler and MCC, the 3-layer. And you see that for long waves, the agreement is pretty great, say up to 2, and then you start seeing some deviation, okay, which is expected. This is the long wave model, okay? Then one thing I would like to bring attention is that it's typical, or many people do this, is assuming the stratification, instead of using parameters rho 1, rho 2, rho 3 for the density of each fluid, you can consider something like this, okay? Rho 1 is just rho 0, which is some kind of reference density, times 1 minus delta 1. That reference density will be exactly the one in the middle layer, and then the lower layer is 1 plus delta 2, okay? And then you can actually, of course, you can always relate delta 2 with delta 1 and say, okay, there's a parameter delta, okay, which is just the one that when multiplied by the other, you get the delta 1, okay? And you can look at how the dispersion relation changes with different values of delta, for example, okay? So here, this is one situation with lambda equals, delta equals 1 or delta equals 5, okay? But anyway, so you have two branches of solutions. By the way, in the long wave limit, you get the solutions, we represent them typically by C0, okay? So you will have C0 minus and C0 plus, okay? For the, I mean, slow and fast speed, okay? Or mode 2 and mode 1. So the linear long wave speeds are obtained by solving this. Okay, as I said, I will use a C0 to denote I'm taking the limit when k goes to 0. Okay, and that b quadratic can be factorized in this way, equals 1. Okay, and I did do this because this particular term here, I can call him gamma, and because you have a product of something which gives 1, then it means that the other term here has to be the inverse of that. Okay, gamma power minus 1, right? Okay, why do I like this? Because this gamma here will appear when you look at, for example, the linear theory or the weakly nonlinear theory. It will appear as the ratio between the displacements Z1 and Z2. Okay, so if you go for weakly nonlinear theory, then you can derive some kind of a KdV equation, okay? So this KdV equation is written here for the upper interface, which we denoted by Z1. So typically Z1t plus alpha Z1 Z1x plus beta Z1 triple x equals 0, right? So this has been set already in a reference frame traveling with a linear long wave speed, C0, okay? And then you have these complicated coefficients, okay? Which depend on all these parameters, plus the gamma that I mentioned just earlier, okay? So this is it. And as I said, if you want to do the same for the lower interface, then, I mean, you can recover it by simply using the fact, the fact that Z2 is just a multiple of Z1, and which multiple? That gamma, okay? So right away, you can tell that, for example, I mean, you look at the first and second baroclinic modes by considering, for example, C0 plus and C0 minus in the definition of gamma. And then what you discover is that mode 1, they have the same polarities, both interfaces, or both displacements of interface, while in the mode 2, they have opposite polarities, okay? And the wave is elevation or depression for the upper interface if you have alpha being positive or negative, okay? This is the case because I mean, beta in this case is always positive, okay? But also very importantly is that according to KdV theory, when the quadratic nonlinearity coefficient vanishes, you don't have internal solitary waves. This is according to KdV, okay? It doesn't mean that in the real situation in the lab, for example, you wouldn't have this, okay? So let's see this. So criticality and polarity of internal solitary waves. So in the slow mode, which is the second baroclinic mode, we can put this in this kind of diagram. So this is H1 over the total depth, H2 over the total depth, and then you can look at when is the quadratic nonlinearity coefficient positive or negative, okay? And this is shaded in gray, which means that for this case, you have a wave of elevation for the upper interface, while in the other case, in white, you always have a wave of depression, okay? And as you vary the stratification measured by this delta here, okay, as you measure this, you don't see too many things happening. I mean, it's basically the same, right? I mean, quantitatively, of course, these things change slightly, but I mean, qualitatively is the same. While in the first baroclinic mode, okay, things are very different, okay? So for this same delta, you get this situation, okay? So which means in this triangle, okay, which is our admissible domain in terms of the parameter region, then you have waves of elevation for the upper interface, and in the white you have depression, okay? And this is remarkably different from this, okay, or that, okay? And that there's actually a transition that is can be discussed analytically about this. Okay, so more exciting things are actually happening at this level for the mode 1 than the mode 2. Now, so we went from linearized version, then weakly nonlinear, and then I'm going to strongly nonlinear. Okay, so I'm studying the steady solutions, right? So in order to do that, I will go to the PDE model, okay, the 3-layer MCC model, and I will start by plugging the ansatz. HI is just a function of x minus CT, UI bar is just a function of x minus CT, the pressure is also a function of x minus CT, and then imposing the typical boundary condition, because I want to recover classical solitary waves. So everything should decay at infinity, okay? So by doing that, I recover this coupled system of second order ODEs, okay? And as you can see, basically it's zeta1, zeta2, which are my variables, and then you have a bunch of parameters, right? So rho 1, rho 2, rho 3, which are the densities, then you have the typical depth in equilibrium, capital H1, capital H2, capital H3, and you have gravity and the wave speed, okay? So, okay, you have a dynamical system, but what is curious is that actually, if you look at the right-hand side of this, so I have rewritten the equations in this way, because the right-hand side, I can look at it as being the minus partial derivative of a certain scalar function v with respect to zeta1, while the other one is with respect to zeta2, okay? So v is indeed a potential for which you can define a Lagrangian given here, and the equations that you have here are simply the Euler-Lagrange. Well, it's not Lagrangian, it's Euler-Lagrange equations, okay? These are that, sorry for the typo. Okay, so, but also it means that you have basically a Hamiltonian system, or is equivalent to a Hamiltonian system with 2 degrees of freedom, okay? So that potential there has been set in order to satisfy these. So we start by saying it's at the level 0 of energy, okay? And of course, the origin is always a critical point, okay? Trivial critical point. So this origin is a non-degenerate critical point for the range of speeds R except those linear long wave speeds, which is C0 and C0 minus and C0 plus, okay? Moreover, we can classify the origin, okay, for that dynamical system. And what we have in this line from 0 to infinity, say, you have C0 minus, C0 plus, which are delimiting the mode 1 and mode 2 waves. And then what you have is, in terms of the surface of the potential, you see that the origin is a maximum of the potential. Here is a saddle, here is a minimum. So in particular, you don't expect to have any solitary waves in this gap between 0 and C0 minus, okay? But of course, they may be there for second baroclinic mode or first, okay? And in terms of eigenvalues, okay, you look at those and you say, okay, here I have 4 real values, okay? Here I have 2 real and 2 purely imaginary, and here only pure imaginary, okay? So saddle-center equilibrium, this is the delicate thing to look at, okay? So here, the existence of solitary waves is pretty much standard thing, okay? It's not a problem, but this one is, okay, saddle-center dynamics. Okay, so then instead of trying to look at the dynamical system and just jump right into the trying to solve numerically, what we did instead is to say, okay, can we look at some asymptotic regimes where the dynamical system is reduced? That was our question. And we could find a few of these. Okay, so one is, for example, saying that you have a small density contrast between two adjacent layers. Okay, so in this case, for example, I will say that the top two layers will have very close densities. Okay, 1 minus epsilon, the density ratio. Okay, then I will put myself in the mode 2. Okay, because I'm considering small wave speeds. And then I expand everything in terms of this small parameter. And what I get is that at leading order, you get that the displacement for the lower layer is flat at leading order, while the displacement of the upper interface is described by exactly the MCC solution, okay, under Boussinesq approximation. And then once you have these, so these are, I mean, asymptotic solutions, right? Then we can go back to the original dynamical system and try to validate that. That's what we have done here. So I put myself in that scenario. So the density ratio between the top layers is close to 1.9, for example. And then I found these solutions, for example, and that's okay. So this one, the one on the right is for a larger wave speed than the one on the left, okay? So you see that as the wave amplitudes, as the wave speed increases, you have longer waves that could, converts to some kind of tabletop solid or a kink, right? So this is one of the things. So we reduced, in this case, we reduced the dynamical system, which was a Hamiltonian system of 2 degrees of freedom. Asymptotically, at leading order, we could find that there is a Hamiltonian system with 1 degree of freedom, which we can integrate, right, as a leading order solution. Okay, let's see another one. So this one is a small density increment across all 3 layers, plus nearly horizontally symmetric symmetry of the domain. So this is the case that was studied analytically. That I mentioned at the beginning of this talk. So these are the very few rigorous results about the existence of these waves. Okay, so if you have all this symmetry, then you can prove the existence of mode 2 waves. Okay, so here we do that, and the leading order approximations are anti-symmetric waves. That's what we get, and then we can go to the dynamical system, the full one, and actually validate. And yeah, we could find these solutions, for example. Okay. We could find this one, we could increase the wave speed, it broadens. This is for waves, what we call the concave waves. And these one are the convex waves, okay, which appear when you have an intermediate layer which is considerably smaller, okay, or thinner. Okay, so these actually remind us the waves that we saw in the train of waves that we saw in the lab, okay, in the movie that I played. Okay, so what other cases can this dynamical system be reduced? So I consider here the case of weak stratification with a sharp density transition layer, okay? So here I'm assuming that you have a constant density increment across the layers, but the intermediate layer is very thin, okay? I leave all the other quantities to be of order 1. And then the corresponding asymptotic solutions at leading order amount to consider the Boussinesq case under the assumptions. The reduced gravities are the same, and the intermediate layer actually collapses. Okay, it's no longer there. So the results can be easily extended for the case when large density contrasts between the liquid layers are present. Okay, but just for simplicity, I'll consider this one. And what you get is that at leading order, you get this. Okay. So you get Z1 is precisely the same as Z2, or you have a decoupled system of all these to be satisfied. Okay, so that's a good thing, right? Because once it's decoupled, then I can easily solve it. Okay, and what we find is that for the displacement of the upper interface, periodic orbits, no longer solitary wave solution, but periodic orbits starting from rest at 0, exist provided C is less than this. Okay, C squared is less than this. So in the same way, we can look at the lower interface, and we can prove that periodic orbits starting from rest at 0 exist, provided C squared is less than this, okay? And then what we do is the following, okay? We want to find conditions for which the period of the upper interface is just a multiple of the period for Z2, or which is the lower interface, okay? And this is it, okay? So this is, n is a multiple that I want to set, okay? And I look at this is an identity where you have here k being the complete integral of elliptic integral of the first kind, okay? So what the first thing you notice is that if you have the top and bottom layer being the same height, then the only solution to this is n equals 1, okay? That's it. So you expect only one, one period goes like this, okay? And but of course, if it isn't the case, then you have all sorts of variation. Okay, so this is the variation, wave speed against n, which is the multiple for the periods. And then the idea is the following. So if n is a rational number, then there exists a unique integer values p and q. Okay, with of course great common divisor is 1. And then if this holds, this condition here, for such value of n, then there is a periodic solution characterized by q humps for the upper interface over p humps for the lower interface within any period between 2, 0 values of Z1 and Z2. So the idea now is that I will take one of these periods, I know that they coincide here, and then I glue it through 0. That's what I do. And by doing that, I build a compacton, okay? And we can prove this in the weak sense. This is a solution to the dynamical system, okay? And these are the compactons that we can produce, okay? And we can see how you can have, for example, one hump over one hump, for example, over 2 humps, or one hump over 3 humps, okay? This is a game that we can play. But this is in a very, how can I say? I mean, this is an asymptotical image, right? I mean, and a very weird one, because you have actually collapsed the intermediate, okay? So how does this resist when we go to finite thickness of the intermediate layer? So we go back to the dynamical system, and these are, for example, here we have 3 waves of this, okay, by increasing the intermediate, the thickness of the intermediate layer, okay? And these are 3 solutions that we found, which kind of look like this kind of solution in the lab, okay? Oh, I said 3, but actually there are 4 solutions. Yeah, 1, 2, 3, 4. Yeah, sorry about that. So this is not in the symmetric case, okay? We have broken symmetry by considering a slight mismatch between the top and bottom layers in terms of thickness, okay? But we still consider that a Bosnian approximation just for simplicity, okay? And then looking at the 2 hump solutions, for example, still the symmetry is broken, okay, by geometry. And you can find, for example, 2 waves like this, okay, by increasing the intermediate, the thickness of the intermediate layer, okay. But of course, this is not, in order to find these, you have to do it properly, right? I mean, with very, very carefully. This has to be finely tuned. Otherwise, instead of a tail that just decays at infinity, we'll get these oscillations, okay. So we are not saying that generalized oscillatories are not there. We are trying to get rid of them, okay? So we are trying to find special solutions for which the oscillations are not there. They can be actually absent. And on top of that, there are some experimental results by this team of Gabrilov and al., who published in 2013 these lab experiments, okay? So clearly you have here 1 hump over 2 humps, 1 hump over 2 humps as well, okay? So these should exist in the lab or in the ocean, okay? So here another exotic solution, 2 humps over 3, okay? And an important thing that we notice is that, okay, so we have a model that predicts not only the existence of these kind of embedded oscillatory waves for which you don't have these oscillatory tails, but also, for example, it predicts something which I was not aware, that you can have a non-unicity of solutions, okay? So if I put myself in this very special case where you have Bosnian approximation plus the top and bottom layers have the same thickness, then the reduced dynamical system enjoys this property. So for mode 1 in particular, this will be very helpful. So if you have a solution, Z1, Z2, then minus Z2, minus Z1 is also a solution, right? And although the KDV tells you that this is a criticality, okay, so you shouldn't have any waves, actually here we find 3 waves, okay? So at this particular wave speed that I pick, and it's something here, okay? So this is where it starts mode 2. This is where it starts mode 1. So if I pick a wave here, I will pick 2 waves here, okay, with different polarities. So one is Z1, Z2, the other is minus Z2, minus Z1, and then I still find a wave coming, okay, from the mode 2, okay. So this is an invasion from slower waves into the faster one, okay. And this is what you have, okay. So if you look at this, everyone will tell you, oh, this is characteristic of the mode 2, okay, but it's actually traveling at a speed which is larger than the linear long wave speed for the mode 1, okay. So in this case, for that value of C, you will have 3 solutions, okay, at least. So, and this happens because you have a very thick intermediate layer, okay. So this is something that we detected. And then, so now, do I still have 5 minutes? I hope I can still talk about this. So these are some recent advances.
You have 5 minutes. Yes, you have 5 minutes.
Yeah. Okay. Thank you.
Sorry, I muted.
So the question is, okay, this is on the level of a model, right? So this is a long wave model, I mean, it's just a asymptotic model. So what is the correspondence between the model and reality? Okay. So in particular, do embedded solitary waves exist for Euler? Okay, that was the question that we raised. And the answer is a very sound yes, okay? So these are some of the solutions that Alex has been able to compute in particular, okay? So all these are embedded, okay? And no oscillatory tails here. And as you can see, this is very rich family of solutions, okay? Not only that, but we can follow these branches of solutions, okay? So this is what we call here embedded solitary wave branches with different density differences. So for example, so we put, for simplicity, for example, assume that the total depth is 1, okay? And you fix here, for example, the intermediate layer 0.25, okay? Then you vary H3, which is the lower axis here, and you follow one of the solutions and you see how it, I mean, how by increasing A, for example, which is the maximum between the crest of the upper interface and lower interface, and you see where these can be found, okay? So this is it. And what you have here is that, for example, those delta 1, delta 2 are just the increments for the density in each layer, okay? So if they have the same, okay, and you have H3 being this, then this is the only branch that you can find, okay? Which is exactly the one that Tung and all were able to show analytically, right? So if you have symmetry, okay, enough symmetry, then yeah, there's a continuous branch that goes, you can increase the wave speed or the amplitude and you will always find this, okay? But if you have, for example, here, then there's only this wave, okay? You cannot just increase it from 0 wave amplitude, okay? You cannot do that, okay? So this is something that we have done, and I mean, we have done it with MCC in dashed and Euler as well, solid, okay? So these can be found, and then, I mean, some comparisons as well, okay? So this is MCC and Euler. Euler is black here, okay? So this is how the sum of these solutions compare, looking at the two models, okay? And here they reach a good agreement, okay? But there are other regimes where they don't, okay? So it's somewhat more subtle, okay, than comparing the two-layer MCC with the two-layer Euler. Three-layer is more subtle than this, okay? And I mean, this is ongoing work, of course, but we hope to be able to report it back to you soon. So I think I'll stop here, and for more information, please check this paper, which was published in JFM. And thank you very much for your time and attention.
Thank you very much, Dr. Barros, for very interesting presentation. Okay, now let's open questions and comments. Do you have any questions? If you have a question, you can raise your hand by clicking the button or just unmute your microphone and directly ask a question. Yes, please. Oh, yes, Ami, please.
Yes, hi, hello. Can you hear me?
Yes, I can hear you.
Hi. Yeah, thanks, Ricardo, for a very interesting talk. Actually, I have two questions. So one of them is more general. So obviously in the ocean, we have more linear certification. So do you think, or do you know how your results can be translated to this case, or in which situation this can be observed? And the second question is about the KDV profile. You know, the picture you showed in the beginning, that, you know, the depression that you showed does not look like a set squared solution.
Yeah.
Is it rather because of the nonlinearity there, or what is the reason for, or can that shape more or less in different regimes be looking similar to the KDV set squared?
Yeah.
Thanks.
Thank you very much for your questions. So I will start from the second question because we are already there on the slide.
Yeah.
So what these tabletop solitons mean is that you are actually approaching not a homoclinic orbit, but a heteroclinic orbit. Okay, it's a front basically.
Yes.
Okay.
Mm-hmm.
So KDV doesn't have fronts. Okay, because when you look at the Hamiltonian system, the potential is a cubic. Okay, in order to have a front, you will have to have a quartic. Okay. Now that can be done by not using KDV, but using Gardner instead.
Gardner. Yeah.
And then you will have that. Okay.
Okay.
But still, the agreement can be quite far from the reality. Okay. In particular, because the front or the conjugate states for Gardner are not the same as for Euler, while MCC has exactly the same conjugate states. Okay. So it doesn't mean you will connect the two equilibria in the same way using strongly nonlinear theory or fully nonlinear theory, okay? But at least the levels are exactly the same, okay? So that's one of the big advantages of this. Now, for the question of continuously stratified flows or fluids in the nature, right?
Yep.
Of course, we are only dealing with those which have sharp interfaces and can be approximated by a 3-layer, okay? Of course, if you have like linear stratification, this model won't work, okay, for sure, right? Yeah. Now, what is remarkable is that if you want to look at steady solutions for continuously stratified flows, I mean, there's already an equation which has been proposed a long time ago for that, right? So the steady waves are described by the Jacotin-Dubray-Long equation, okay? So that's an eigenvalue problem, 2D. But the problem is that although you can solve it for mode 1 waves, and there are numerical codes for that, for example, by this team in Waterloo, Kevin Lamb, for example, Alex Dasna, right? I mean, the code is available to anyone, right? Yeah. But you can do it for mode 1. For mode 2, there is no such thing. Why? Because in general, they won't exist. There will be always these oscillations, okay?
Yep, makes sense. Thank you very much. Thank you. Thanks.
Thank you, Amin. Any other questions? Okay, then I'm going to ask a question, Ricardo.
Yeah.
Yeah, I think it's a numerical computation. You have to truncate the computational region in the horizontal direction. Is it correct? Do you have to truncate?
Yeah, of course.
How did you set the boundary conditions at X and?
Okay, that's a good question actually. So as I said, to look at for in particular these multi-hump solitons, okay, things like this. So for example, these kind of things, okay, they cannot be tracked by looking just simply at the embedded solitary waves. So you have to go to generalized solitary waves to try to track them down there, okay? So you use the idea proposed by Alan Champneys by looking at the curvature at the end of the domain, okay? If it is positive, if it is negative, it means that you have passed through 0, okay? So when you have one of those with 0 curvature, then you can actually expand your domain. You can double it, you can triple it, you can quadruple it, and see how robust is this. And if it is always the same, then it means that you are on the right track. That's basically what we do. Yeah, we change the domain, and we don't have to double. We can extend it just simply, right?
Okay.
To avoid these troubles. Yeah.
Okay. Oh, thank you. Any other questions? Okay, thank you very much, Ricardo. Very nice presentation, and thank you very much for your contribution.
Thank you very much.
Thank you very much. Okay.
I will stop sharing, okay?
Yeah, please.